Hi, my name is Jonathan Freund. I'm a professor here at the University of Illinois, and I am the co-director of our new center on the exascale simulation of plasma-coupled combustion. I co-direct the center with Professor Bill Gropp in computer science here, and it's housed within the Parallel Computing Institute in the Coordinated Science Laboratory. It's part of the PSAP program, which is the Predictive Science Academic Alliance program from the DOE. And we are investigating how plasmas can be used to control combustion.
What is plasma-coupled combustion, John?
So let's start with regular combustion. And in regular combustion, you need fuel and oxidizer to mix. They need to burn, and they produce their product. And we can engineer flow rates. We can engineer the geometries of that surround the combustor, but we don't have any control over some of the key parts of the mechanism, including the chemical pathways, and we can't put heat right where we need it at the right time. And plasmas can do both of these things. The species created within a plasma can short-circuit the normal chemical reaction pathways of combustion, and a plasma can deposit heat directly where you need it in an engineering application.
What are the needs?
So there are many opportunities in society to use plasma to benefit things. There are the high performance needs. It may be an enabling technology for, say, a hypersonic vehicle. It can lead potentially to higher safety of civilian aircraft. And it can work in vehicles like your car, for example. A spark plug is an example of a plasma, but we could potentially tailor that to make combustion cleaner or more efficient in even your car.
What does the extreme scale computing provide?
So yeah, extreme scale computing is a critical part of this center. Any plasma combustion system is extremely complicated. There are multiple physical things that are going on within it. You have reaction, turbulence, electrodynamics of the plasma. And these entail a huge range of length and time scales. And we want to represent these with a high degree of physical fidelity, realism. And so extreme scale computing allows us to represent them grounded in physics. That's one thing. Another thing is it allows us to do many simulations so that we can study inputs and outputs. And so even within a high fidelity physical model, there's some assumptions. We can study statistically how those affect the output, and we can then assess how uncertain that output is.
Why is that important?
Well, ultimately, any prediction is done to inform decisions, and presumably they're important decisions. So that's the kind of the foundational region. It's important to represent the physics because it provides a robustness. If you design a model grounded in physics, it has a much better chance of applying an accurate prediction in cases where those same physics apply. It provides a robustness to that. Why assessing uncertainty is important is because it adds tremendous value to a prediction. If the decision maker gets a prediction along with some measure of how uncertain that prediction is, that gives much more value to that decision maker. They can draw on more information than that.
What will it take to utilize extreme scale resources for such an application?
So we are designing our mathematical implementations of these physical models in kind of a unified framework, a kind of a structure of sorts that will allow us to access the computer science tools that will also be developed within the center, and that will provide a bridge to getting it to run efficiently and effectively on these forthcoming computer systems, which extrapolating into the future will be heterogeneous and very complicated. And a close collaboration across the center between the application physicists and the computer scientists within the center will be key to making this happen.